Welcome to Lecture 20 of Graduate Probabilistic Programming. We're going to talk about deep probabilistic programming today in UBC's CS532W, Graduate Prob Prog. I'm Frank. This is us. We'll have fun. Okay. Last lecture in a reasonably interactive lecture. Everybody's still a little bit too quiet, but that's okay. Last time we talked about model learning, really, right? That was what we started talking about. We said, hey, what if we don't have the ability or the knowledge to write down a particular generative model? Shouldn't we learn it from data? And we said, okay, well, let's set up some objectives that allow us to do model learning. In particular, we talked about using stochastic gradient descent or gradient descent writ large to do model learning, basically doing EM. We talked about the IID data setup. This is, of course, framed as simultaneous model and inference network learning, right? In practical circumstances where you have to use some sort of proposal distribution, that's the inference network thing. And we looked at a couple of old school things like the Helmholtz machine, the variational autoencoder, although we skipped over the reparam version of that. We talked about wake sleep, Roux-weighted wake sleep, so on and so forth. And today we'll talk at a relatively high level about what deep prob prog is and really like introduce it in its finality in some sense. Touch on reparameterization, talk about VAEs, and all of this will basically be in the flavor of stochastic computation graphs, although we'll do it just from deep probabilistic programming. We won't do deep stochastic computation graphs. So we've talked about a couple of different strategies for learning the variational distribution Q, which is for model learning, simultaneous model learning, and so on and so forth, right? Both strategies, minimizing the inclusive or exclusive KL, whatever, both strategies use Monte Carlo to estimate a gradient of an expectation. The first strategy, the variational inference strategy, the KL in this direction strategy, minimizes the elbow directly, right? Fine. Right. So when we minimize this as an expectation with respect to the variational distribution, what we showed, particularly in the BBVI section of the course long ago, is that we needed to use a likelihood ratio estimator to approximate the gradient of this expression. In other words, in order to move the gradient inside of this expectation and rewrite it as an expectation at the end of the day, we ended up with a form that looked like this. This was your BBVI homework, right? And this can have high variance, and if you actually ran BBVI long enough, you know that it can take a little while to learn the parameters lambda because this is a high variance gradient estimator. We also said we can actually not do the elbow thing, right? We can not minimize this KL and average it over Q, right? But we can minimize the other KL, which is got the model in the first position and the inference network in the second position, and average that over observations, right? We talked about that last lecture. When we do that, we don't need to compute a likelihood ratio estimator. Posterior doesn't depend on the variational parameters, but we have to perform importance sampling to generate posteriors from the posterior, right? Fine. So we can definitely do this minimizing KL in this direction to learn inference network parameters. It's not a problem. But there are other problems related to the fact that you're doing importance sampling, biased estimators, and so on and so forth. And particularly if you don't do the wake phase sleep update, which we actually didn't go over in lecture, but is pretty straightforward, and you only sample from the model, then it may be that your inference network, your model is not well enough learned to actually provide good learning signal for your inference network. And the whole simultaneous model learning and inference network learning pile of cards can come tumbling down. So this lecture, we'll talk about a third strategy, which makes it possible to actually learn the exclusive divergence, which is, of course, this KLQP divergence, with a comparatively a relatively smaller number of samples. And the way this works is to use reparameterization to re-express the expectation with respect to Q in terms of an expectation with respect to some distribution that doesn't have any parameters, a parameter-free distribution like a normal 0-1 distribution or something like that, which simplifies the gradient computation. This kind of derivative is known by a bunch of different names. One of them is the pathwise derivative, right? And it's used very widely in sort of normal variational autoencoders, with continuous latent variables. But you can use it in stochastic computation graphs with continuous reparameterizable nodes. Random variables. Yeah, awesome. Hey, Emma, how are you?
Hi, good. How are you?
Hey.
So I just joined in, so maybe I missed the explanation. But the pathwise derivative, does it have connections to the directional derivative? Is it the same thing? Based on the name, it's not the same.
No.
Is it connected at all?
No, I don't think so.
Okay, thanks.
If you see that it is and I'm wrong, please tell me, and then I will answer that question differently next year. Is that a potato?
It's a green scone.
like it's a whole new level of joke down. I'm just eating a potato. Hi, Mia. Okay, so you've come just in time. The basic idea, just to catch up, is that we're talking about simultaneous inference network and model learning, and we just said, like, there's this exclusive divergence. We can call it the mode-seeking divergence, so on and so forth. We can do this. This is the sort of the VAE thing that you're used to in some sense, or would be used to. And this is the sleep phase of wake sleep. We can minimize the other KL divergence and learn the inference network with this KL divergence. And we can do model learning under the elbow or whatever. It's just gradient descent then. So if we want to use the exclusive divergence for whatever reason, and there may be some reasons to do that, then there's a different strategy besides doing this this likelihood ratio reinforced gradient thing, which is high variance. What we can do instead is reparameterization. And reparameterization is conceptually quite simple. There's some finicky details that you can pay attention to if you want to. So we'll just illustrate the idea of reparameterization, then you can go into the details for specific models. But in fact, actually, if you back it off to a computation graph, it really almost always comes back to a simple example like this. Depends on what your primitives are. So suppose that we have a variational distribution Qx lambda on a single variable. Now we're not in Prob Prog land, we just have a single variable that has a form of a Gaussian with parameters. Lambda is the mean and the variance of the standard deviation of the Gaussian. So we can sample from this distribution, this normal distribution Q, right, by doing what you would do anyway, right? You can apply a deterministic transformation. We're going to uniformly use the notation G to this random variable epsilon, which comes from some distribution with no parameters. So epsilon here is just going to be normal 0, 1, right? And in order to get a sample from, normal x over q is the same thing as normal mu sigma squared, then the way we do this is we draw a normal 0, 1 distributed epsilon, and then multiply it by sigma and add mu, and this is this deterministic transformation. Okay. So this construction ensures that x is a Gaussian variable with mean mu and standard deviation sigma. In other words, computing x from a randomly sampled epsilon is equivalent to sampling x directly from q, where q would be this normal mu sigma distribution. And we can check the first two moments in the standard way. Take the expectation of x. We know that that's mu, right? This is 0. The variance of x is just the variance of sigma times epsilon. That's the sigma squared. Okay? Simple, simple. What's super nice about this, though, for optimization purposes, is that we can take, so now we have some function r of x. We can rewrite an expectation of this function with respect to q in terms of an expectation with respect to a base distribution, or whatever you want to call it, a distribution p epsilon that has no learnable parameters. Okay, so obviously you probably are remembering that r for us is going to be something like the log joint over log joint over inference network. But for now, just think this is just some expectation we want to compute, right? And we can compute this expectation with respect to q by just saying that, well, x we know is a deterministic transformation of this random variable epsilon, and we can just say, okay, let's sample over epsilon instead, push it through. That's the same thing as sampling from x. So this expectation over r of x is the same thing as taking an expectation over epsilon and then transforming it with g and pushing it through r and then averaging. Okay. So if we want to, as we do when we're doing variational inference, learn the value of lambda for whatever reason, right? Again, this is just some expectation that we'd like to optimize with respect to lambda using gradient descent, then this reparameterization trick is how it's called. Just change a variable, really, is useful when we want to compute the gradient of this expectation with respect to lambda, because the distribution from which we're sampling here has no dependence on lambda anymore, right? So we can express the gradient, so the gradient of this expectation with respect to lambda is just equal to the gradient of this expression with respect to lambda, which is just an expectation with, so basically the gradient can pass inside this, right? So we've got an expectation with respect to p epsilon. And then the gradient operating on this expression, r of g of epsilon, just requires you to use the chain rule, right? So we have the Jacobian of r with respect to x. If this is just a we can think univariate or multivariate. We've been saying univariate, so I should just say the partial of r with respect to x evaluated it at the value of x equals g epsilon lambda times the gradient of g with respect to lambda, or the partial with respect to lambda. Okay, so this is literally just the chain rule, but done in multivariate form. Okay, this makes sense. It's like the first time I've ever done something slowly enough that it actually makes sense. Just remember this moment for your teaching evaluations. Just remember it. He was clear. Okay. I put this slide here. I don't know where the right place to put this is, but like y'all were complaining about the BBVI stuff, so I felt really bad about it. So I did a bunch of LaTeX for you just to like eventually we're going to be doing something here where this is going to be indeed multivariate, right? So we have some x that's going to be multivariate, and we're actually going to be computing this gradient, and we're going to have a bunch of our reparameterized variables, blah blah blah. So I'll just say that the form of this chain rule in Prob Prog, right? In particular, when we, this should be capital X, sorry about that. Yeah, there's a couple of notational things that I should have fixed here, but that's okay. Capital X, and this would be X alpha for all alpha, basically. Anyway, so if this is evaluated over some X as defined in the book, and we've been talking about all the random variables in a program, and there's a vector of parameters for all of the reparameterization kernels, like these G functions that we've been talking about, right? Then the shape of this is like there's a vector of partial derivatives here, where you take the partials of R of X with respect to every addressed random variable, evaluated at the transformation of that random variable from a parameter-free proposal, and then provided that your push forwards G are not dependent on one another, then the Jacobian factor here looks like it's just a big matrix that looks like this, right? So there's no derivatives on the diagonal, on the off diagonals, and you have a derivative expression that looks like this, where you have the partial with respect to every address, and then every address random variable with respect to its transformation parameters. Okay, you can go back and look at this if and when you ever care. The point, though, is that now, thanks to the reparameterization trick, we can estimate the expectation that we want, if indeed we want to take an we can estimate the gradient of the expectation that we need to compute by doing Monte Carlo integration, right? Which is to say that provided that we do the chain rule out, we use autodiff, whatever we want, right? We have the partial of R, and we just plug in the values of epsilon drawn from Q epsilon, right? It's sort of obvious, P epsilon, excuse me. So basically, all it's saying is do a Monte Carlo approximation of this thing by sampling epsilon from whatever the distribution of epsilon is for every address. Okay. Does this make sense? Is that a question, I mean?
Yes, I wrote a question in the chat in slide 8.
Sorry, yeah.
Why does a lambda have a subscript? Aren't the reparameterization parameters same for every x in big X, like every random variable?
No. So if you're talking about it in this particular case,
Yeah.
yeah. So every random variable so think about the random variables that are addressed in a program, like they're literally nodes in a graphical. Like think about the FOPL context, right? You're gonna have nodes in a graphical model, right?
Okay.
So they will have a link function, right? But every node will be of a different type. It'll be a normally distributed quantity, or a gamma distributed quantity, or a Poisson distributed quantity, or something like that. And I've given you one example. This is a good question. Thank you for the question. It's a really good question. I've given you one example of a transformation, right? It's a very typical transformation. You can go off and look up transformations for different distribution types, right? So Gaussian, I've just given you univariate Gaussian. It's pretty obvious how you would do multivariate Gaussian. Poisson, gamma, Dirichlet, like all of them have, basically all exponential families have recently all exponential family distributions have these kinds of transformations that you can do. They're not obvious, and that you can look up libraries of them basically. But the point is, indeed, in this, there will be a different distribution type, i.e. a different transformation that you apply to every random variable.
Okay,
To
thanks.
produce via deterministic transformation of the random variables of those types, I should say. I
Can I
see
ask questions?
Yeah, of course.
Yeah, so I was wondering, like, do people do this for like BBVI if all your variables are continuous, or is that literally what we're doing right now? Like, have people just done BBVI without score function, but with reparameterization?
Yeah, that's yes. So there's a whole stack of papers, and to be perfectly honest, I lose track of what the deal is with each of them. There's stochastic variational inference, there's black box variational inference, there's automatic differentiation variational inference, and they all kind of come down to the same thing, which is either you use reparam or you use reinforce. Those are it, and whether you can differentiate through or not. Deep probabilistic programming, writ large, is simply variational inference where Q and P consist of a mix of discrete and continuous random variables. So everything just slams together because you're just doing variational inference, which is just joint model learning and inference network learning. And if you have Q on the outside, so you're doing the exclusive KL, or the mode seeking KL, mode seeking KL, then great. You have to differentiate through Q, and if Q, you have to differentiate through an expectation over Q, and if Q is all different, like all continuous, then you use reparam, and that's a VAE. If it's all discrete, then you, like in reinforcement learning, then you do reinforce, and if it's a mix, it's a mess. And that's what deep probabilistic programming is. And that's really all we're going to do today. It's like, okay, how do we deal with this mess when we have a model that has a mix of these two? And can we do it automatically? That's it. So for now, what we're saying is that all of these, like all of them are everything in Q is reparameterizable, which means that we're basically in the VAE case, except that in the VAE, there's only one random variable, and it's usually multivariate normal, so there's only one reparameterization that needs to happen. So what we're talking about right now is some sort of structured VAE where all the random variables are reparameterizable. So already you're doing something that's now very, very state of the art. You can take your FOPL program, write out whatever structured VAE you want, and use reparameterization of the kind that we've just showed here, and do simultaneous model inference network learning in FOPL programs with reparameterization. You still have the problem of discrete random variables. That's still problematic. And it's kind of interesting to think about, it's actually more than interesting to think about control flow also. So there's a little bit of a wiggle room for control flow because there's still some even in FOPL models with control flow, you still are not differentiable everywhere. So there's some interesting optimization questions to be asked. Fine. So I would say, really, you want to be thinking evaluation based, so you can compute the gradient at the current sample value, and then who the hell knows what's going to happen when? Who the heck knows what's going to happen when you take a gradient step, because you might not be differentiable everywhere thanks to control flow. Or sorry, continuous everywhere. Sorry. So if we want to think about this reparameterization technique in terms of the variational objectives we've been talking about, we can consider the case where the expectation that we're taking is with respect to a function r here, which is got y, x, theta, and lambda in it. That's totally fine. Nothing controversial here, right? That's just the log joint over the variational proposal distribution, which results in a okay. There's a bug, a reparameterized elbow of the form given here. Okay. So all that we've done is say, okay, if we can, for all of our x's or for a single x, reparameterize, then we can replace the expectation over q with an expectation over epsilon and replace every x with its transformation. That's it. So relative to the likelihood ratio and importance weighted estimators, these reparameterized estimators tend to have lower variance. And in fact, often it's possible to use to get decent elbow estimates using a single sample from P epsilon, which is pretty cool.
Can I ask a question?
Please, somebody should ask a question. Mia's not asking questions, so you know.
Can you do this sort of like in a Prob Prog sense? Can you do this sort of mix and match between discrete and continuous random variables, that you reparameterize all the continuous ones and you just do score function for all the discrete ones? Is that possible?
Oh yeah, that is the leading question of the lecture, and that's really basically at this point that's what I'm teeing up, and like just get ready for it because it's hideous and horrible. Yes, that's what's coming.
Gotcha.
So, to Amin's point, the concept of reparameterization is not unique to Gaussian distributions, right? The requirement for reparameterization, the main one, is that we have to be able to define a differentiable transformation, right? And for many continuous univariate distributions, anyway, we can transform a variable epsilon that is uniform on the unit interval using the inverse of the cumulative distribution function, right? It's sort of obvious that would be true. You just look up on the inverse cumulative distribution function, which is often analytic for univariate distributions. Fine. So reparameterization broadly is possible even for certain distributions where inverse transform sampling is not stable. Gamma, Dirichlet, so on and so forth. And there are references that you can look at if you become interested in reparameterization. The problem, though, is that reparameterization is only applicable to continuous variables. It is not applicable to discrete random variables. So it's true that you can write such a transformation, generally speaking, but that transformation won't be differentiable. Right?
That's a good question.
Yeah.
So in my head, this sounds like it's a similar concept. Like reparameterization sounds like it's a similar concept to in convex optimization, where you have a problem that's non-convex, but it can be transformed into a convex problem and the problems are equivalent. Is it a similar sort of idea? You're transforming it to making it more tractable?
I like the intuitive leap and thinking. I'm not sure that it's quite the same. Really, in some sense, this is all much ado about nothing. It's in some sense like here we're really specifically talking about. At the end of the day, we really want to be able to do maximum likelihood. That's really what we want to be able to do. We really want to be able to maximize the marginal likelihood, this log Z thing that you're computing in SMC, but not actually using right now yet, right? We really want to be able to maximize this with respect to with respect to the model parameters, right? So that's the problem. So it's a general trick in some sense, but the reason for worrying about this reparameterization trick thing is that we can't integrate. So that's the first thing. And when we do importance sampling style integration to estimate the evidence, then we have this structure where we have to take, if we want to do maximum likelihood, we have to take a gradient through something that looks like this, right? And as soon as you take a gradient through something like this, it is no longer in the form of an expectation, which means that you would have to do some sort of, like, we don't know how to compute an average. We don't know how to do stochastic gradient if it's not in the form of an expectation that we can, estimate via Monte Carlo, right? So all of this is really just how can we turn our optimization problem into the form of something that takes it into the form of an expectation.
And then, like, the solution is going to be the same as the solution you get from your transform problem is going to represent the solution for the original problem, just in a more computationally tractable way, so that you can use this maximum likelihood.
In particular, the reparameterization just allows you to be able to take a gradient of this expression with respect to lambda, because the thing in the expectation is not a function of lambda. So you can take the gradient and pass it in. That's all this trick is doing. So yes, the solution, the gradient, the Monte Carlo estimate of the gradient is the same in expectation.
Okay, yeah, so they're equivalent problems, just one we can solve in the ways that we have.
We can solve both, right? So we can also do, sorry, let me go back to it. Where was it? This. So this is the same, right? It's just another way of rearranging things so that the gradient after this BBVI thing, the reinforced estimator, arises from doing the derivative of log equals 1 over the thing, like that trick emerges. The only reason why we did that is so that we again could express things in terms of an expectation, right? And the gradient here is here. So the gradient is already passed in, and it just so happens that we rearrange it so that there's an expectation here, right? So what we're really asking is, which of these gradient estimators is better for optimization? And something that people have focused on in machine learning for a little while is the variance of these gradient estimates, because of course in stochastic gradient descent, if your gradient estimates are really all over the place, it's going to take you a long time to converge, right? And it is empirically been demonstrated over and over and over again that if you can, you should always use a gradient estimator of this form, because it's much, much lower variance. So the expectation is the same, but it's a lower variance gradient estimate. But you can't do this unless the conditions for reparameterization are satisfied. Okay. And those conditions are that your model is differentiable with respect to x, right? Because you've got a chain rule term that's gonna pop out here, right? And there's a differentiable, and the transformation itself is differentiable. So G here would have to be differentiable as well, right? Also because of the chain rule. Okay. Okay, I think that's the same thing as before. Yeah. That's what I just said. So it's possible to find, yeah. The second requirement that you have is that this is not just differentiable with respect to theta and lambda, but also has to be differentiable with respect to x. So how about we take a 5-minute break and then we'll come back and deal with the mess. And we're back. One of us I know is capable of heavy lifting, so let's see if we can all do it. Anyway, so pathwise gradients. So referring back to what I talked about before, the second requirement, because of the fact that there will be a chain rule term here, is that the model density is differentiable with respect to x, right? And this is the significant implementation challenge that arises when using reparameterized estimators for variational inference and probabilistic programming. So unlike the BBVI likelihood ratio gradient, this pathwise gradient requires a differential model density, since the multivariable chain rule says that the gradient will contain this term, which is what I just talked about, right? So this implies that naively reparameterization can only be used in situations where the model density is itself differentiable with respect to the latent variables. Okay. So we've already dealt with this. So I misspoke the other day when I talked about Hamiltonian Monte Carlo, because the other one was black box variational inference. Are you guys chatting and having really hilarious conversations while this is going on? Because everybody's laughing. I'm seeing some chatting going on. That's good. Okay, all right. Just put it on the chat channel so I can see it. It's going to be funny. Just make it funny for everyone, even if you're making fun of me. It's great. Yeah, I promise it won't affect your grade. As it happens, we have actually already dealt with this situation. So where we need the gradients of the model density with respect to x, that's Hamiltonian Monte Carlo. Okay. So now what we'll do is talk about how to deal with gradient-based learning with both reparameterized and non-reparameterized random variables. Yeah. So dealing with this, we're not going to make this homework number 7. But dealing with this is deep Prob Prog. Okay. So this is the main point. When we're computing the gradient of the lower bound, this is Barron's question, is that the probabilistic program can contain and will contain in general a combination of continuous and discrete variables. And ideally, for the continuous distributions, we'd want to employ reparameterization whenever possible, because it reduces the variance of the resulting gradient estimator. But for discrete variables, really the only thing that we can do is to compute likelihood ratio estimators. It turns out, and this is really quite nice, is that there's actually not a problem with combining them in a single proposal. In fact, we can define a single objective that computes the correct gradient estimate for each variable in the model, or each parameter in the model. And this is very closely related to foundational work on stochastic computation graphs. So really everything kind of came together at the time of stochastic computation graphs. And what does this look like? In probabilistic programming, I would give Daniel Ritchie and web people the credit for this formalism, and then my postdoc Jan Willem for doing it a slightly different way, ending up at the same place, basically at the same time. So to explain what's going on, we're going to use the convention introduced by Ritchie, which allows reparameterized and non-reparameterizable variables to be expressed in the same common notation. So let's consider some case where we'd like to sample from our proposal distribution Q for some variable x parameterized by phi by transforming a sample from some base distribution. Okay, so in the earlier example, just to be concrete, this would have been normal 0, 1, and then G would have been G of x. Phi would have been equal to mu x plus epsilon, where mu and epsilon are part of phi. So we're switching to phi versus lambda. Doesn't really matter. Fine. So we're going to transform from some base distribution, which we're going to call Q tilde. And that's going to be the one corresponding to x. That's Q tilde of x is going to correspond to x. And then x tilde is going to be pushed through G, and both G and Q tilde can depend on the variational parameters phi. Okay. So we're going to call this the base distribution as well, and this the transformation. Okay. In this way of looking at things, it's just a formalism, a notation, we can consider reparameterized and non-reparameterized distributions as special cases. So reparameterized proposals combine a parameter-free base density, Q tilde x tilde, with a parametric transformation. Okay, so in other words, notice that Q tilde x tilde does not have phi in it, right? In other words, the gradient of Q tilde x tilde with respect to phi will be 0 because it has no dependency, right? Okay, so Q tilde x tilde normal 0, 1, and the parametric transformation does take phi, so G x tilde phi would be phi mu x, phi sigma x, whatever, x tilde, right? Non-reparameterized proposals combine a parametric base density with a parameter-free transformation, which is taken to be just the identity function, okay. Which again, x equals G tilde of x equals x tilde. There's no phi here, so the gradient of this with respect to phi is 0. So if you have a discrete random variable, x distributed Bernoulli, in other words, we have this in our inference network, and we need to make some proposal, then we can just say Q tilde x tilde is Bernoulli, and then just map it without transformation through G. So in other words, we assume a notational convention in which there's always a dependence on data in both the base distribution and the transformation. But in practice and in reality, we'll use distributions for which either the gradient of the base distribution with respect to its parameters is 0, or the gradient of the transformation with respect to the parameters is 0. Okay. So it's a little bit tough to keep this. I have a very hard time keeping this in my head, but let's try to remember as a group, and you'll have to help me remember that reparameterized proposals, like reparam proposals, parameter-free base density, right? Parameter-free base density, this is the case. Non-reparameterized have a parameter-free transform, right? Meaning that this is the case, and the gradient of the transform is 0. Okay. Cool. So we can use this notation to define a general lower bound that encompasses both reparameterized and non-reparameterized terms. So suppose that we use this Q tilde x tilde, big X tilde, given y and phi, to denote the base proposal for all variables in the probabilistic program. And the density of the probabilistic program, as in the book and everything so far, is this joint distribution over y and x, right? And we use G of x tilde y, big X tilde, big Y, phi, to refer to the transformation of all of the variables. So there's going to be a transformation, just again, for, like there's going to be a different transformation for every random variable, different type transformation, so on and so forth, right? But we just have, a transformation of all the random variables. Then we can define a variational lower bound of this form, right? We could just, this is what we've seen, right? It's an expectation over Q tilde, in other words, the base distributions, right, of log of W, Y, X, big X tilde, phi, where this weight, we'll call it importance weight, that's fine, is defined as the joint evaluated at the transform of X tilde, i.e. X, right? And the proposal distribution evaluated at the transform of x tilde, which is, again, just x.
Can I ask a question?
Please, absolutely. I want people to ask questions, as you know.
This Q tilde is just a product of all the distributions that we saw in the previous slide. Is that right?
Yeah.
Yeah, okay.
You mean the previous slide? Yeah. So for every individual random variable, for every address, it gets a little bit hairy, right? Like it's almost impossible to write this down. You really have to, like, the only way to really instantiate this is in code, right? So we're talking about something that has to be a little bit notationally vague, which is uncomfortable for everyone. But if it isn't, it's just hideous, right? So think addresses, right? There's an address set of random variables, and you really should be thinking traces even, right? Because this doesn't make any sense in the non-trace context, because you need to be able to compute a gradient at a particular value, and we're going to be looking at a particular value, right? So addresses, traces, there's a transformation there's a transformation for all variables, one of which is identity, the other of which is actually a transformation. Yeah. I mean, sorry, can't see me looking at you.
Sorry, can I ask a question?
Yeah, of course. Yeah.
Why do you want the gradients to be zero? Is it something related to like being able to compute a gradient with respect to only the parameters and not with respect to the
This is
themselves?
a leading question, and yes, this should be the principal curiosity. It's like, why are we setting up a notational framework for doing this? Yes, this is what's coming. Hang on to your boots for just a second. We're getting into a deep squat position, about to do the serious pushing. Anyway, okay. So when we compute the gradient of this bound, as always, we're going to get the terms that we should be familiar with at this point, right? When you expand it out, we get the you get all the terms, right? You get the reinforced terms here, and you get this is just again chain rule. We've done this like 6 times already in the course, so I'm not going to do it again. But it's just chain rule on this. Okay. So you obtain these terms, right? So the first term, and this, I could almost stop here and just say, okay, check it out yourself if you want to, because it's now you just have to go believe it, right? The first term of this, because of the way we've set things up, computes the reparameterized gradient estimates and will be 0 for any non-reparameterized variables. The second term computes likelihood ratio estimators for non-reparameterized variables. But because of the way we've set up the notational convention, it'll be 0 for non-reparameterized variables. Okay. And we can let's go ahead and look at it if you would like. So the loss from the previous slide looks like this. Again, notational shorthand, remember that Q is a function of phi through the reparameterization, right? So I'm dropping all of the phi's because again, it would just be too much. Okay, so the objective that we're trying to optimize is this expectation, and we reparameterize it. So we're using Q tilde instead of Q, which means that we're evaluating P and Q for the reparameterized variance, right? So we take a gradient of this, right? Then what we're doing is we're taking a gradient of this expression, which is just a gradient of an integral. So I've just swapped the integral and the gradient here, and we've got Q tilde here, and then the log transformations dx tilde. Okay. And again, what I said I wouldn't do, but if you want, when we take the gradient of this, right, we have the product rule, which gives us these two terms, right? So the product rule is we take the gradient of this, okay? And we have with a gradient of this, we know that that's equal to q times grad log q. So that's what we've done here. And this is just a copy of these down. And we have q times the gradient of this. Okay, that's what we've done here. Okay? So product plus the reinforced trick. Both of these now are expectations, like I've talked about with respect to q tilde. So our common notation for expressing parameterized and non-reparameterizable and non-reparameterizable random variables in the same framework, right? Okay. Fine. So that's all I've done. I've just rewritten this as an expectation, right? So the whole point is that if q tilde is reparameterized, right, then q tilde has no dependence on phi. That's the whole point. We've set it up. We've set up the notational frameworks in this way, right? So it's reparameterized, which means that q tilde itself is like normal 0, 1. It's uniform 0, 1, something like that. There are no parameters in it, right? So the gradient of q tilde with respect to the parameter, the inference network parameters phi, is 0, which means this term goes away. These two terms are left. That's totally fine. Right, so this is what will be computed for all of the reparameterized variables, just as promised, right? If q tilde is not reparameterized, then by the convention we adopted, the transformation is parameter free, so that this partial is 0, right? So if we look at this term, and we just do the standard thing, right? We just take the partial of log p gx tilde, right? It's 1 over p of gx tilde times the partial of p evaluated gx tilde dgx tilde times dgx tilde d phi. Okay, this is just chain rule, straight across, right? But this thing for non-reparameterizable variables is 0. Because by our assumption, this thing is 0, okay? And when q is not reparameterizable, you can note that this expectation under q tilde and the transform is the same as the expectation under q. Doesn't really matter. This step doesn't really matter, but it's the same as the expectation for q, and this is the same derivation that we've done several times. That this is basically the expectation of the score is 0. Okay. Cool. So that's it, really. We can do a.
Sorry, before you move on, if this is all there is.
This is all there is.
Well, no, I like
programming. Done.
I thought that you were gonna get to the question that I was I'm gonna ask now, but you weren't, so I'm gonna ask it. So at this point, like it's really cool, right? Because you can sort of like divide up your variables in one and the other, but like practically, what do you do, right? Because q tilde is now this product of all the random variables, and for some, I'm just trying to think out loud. I'm not sure I have my question completely coherent. Is it just like as simple as summing up the reparameterized gradient for the reparameterizable variables and the score for the non-reparameterizable?
So there's a bunch of ways that one could implement this, right?
Mm-hmm.
right? One way is indeed just to say, okay, well, we know that this is the case, so just actually only compute this bit for the reparametered variables and this bit for the non-reparametered variables, and you're done. Or you can make your distribution library come in this form. And then just auto-diff the loss.
And just take for granted that autodiff will take care of setting the right term to 0 for you. All right. Simple.
Ish, yeah. So there's more stuff. If you read the Ritchie paper, there's more stuff about like automatically setting up control variates for subgraphs of the computation. There's lots of stuff. But at the end of the day, it really comes down to you really want to take the gradient of this thing, right? And so long as your G's, your transformations are set, basically all of your distributions are parameterized, reparameterized, or parameterized in this particular way, where you actually have a G, right? That is either the identity or something like this, right? Then you can just auto-diff this thing.
Right.
Anybody want this to be homework number 7?
Will it replace the project?
One of the projects is actually doing this. So the one project is effectively re-implement Pyro, which is literally just to refactor what you have to do this. Right. So we can do a concrete example if you want to, or we can actually leave early for the first time ever, or whatever, right? But I I hinted at this web people design. I haven't showed you Pyro design, but it's sort of, I guess, somewhat evident, I would guess, because we have P and Q that are separate. But the web people style proposal was to interleave Q and P at the same time in the same program, right? So consider a program P, which has some sort of web people style proposal for continuous variable V and a discrete variable Z, right? So what is this, right? So there's some random variable Z that's a priori distributed discrete uniform over 10. There's some continuous random variable which takes Z as its mean. There's some link function which we might want to learn. This would be part of theta, right? Fine. And then we observe under some other link function we might want to learn with mean V some data Y. Okay. Simultaneously in this program, there's also an inference network whose parameters we might want to learn. So the inference network has a discrete proposal with some with a link function that takes Y and phi and is parameterized by lambda Z, some neural network. You want to learn those parameters. And V also has a proposal distribution, which takes the value of Y and Z and has parameters phi, which is some neural network lambda that produces the proposal mean and proposal standard deviation. Okay. This makes sense? Jason, does this make sense? Ryan, makes sense? Okay. Cool. Fine. What does propose look like in the general case? Right. And this is getting to sort of like what you would do in your distribution library. So your distribution libraries, as they are, look a particular way, but propose is going to need to be able to produce this ratio for autodiff, basically, right? And you can probably guess what propose should do, but one concrete implementation of propose, given these two distribution types, right, is to basically look up the distribution, which will give you a base distribution, a transformation, an inverse transformation, and a factor for change variable, right? You do that for dq, and then propose would sample from q tilde, and then pass it through the transformation for q tilde. So for a discrete variable, this would just be a parametric sample, and then this would be an identity, right? For a reparameterizable variable, this would be a parameter-free thing, and this would be some distribution-specific transformation. And then, of course, the factor that you put on is the necessary probabilities, the probabilities that correspond to these p of g tilde x's, right? So you would be sampling in transformed variable space, right? Pushing it through a transformation, but you do need to actually score in the original program space, right? So you only have the base distribution, so you need to transform back the sample value back into the base distribution and then do a change of variable to get just p of the probability of the this is equivalent to p of x. Okay. This is equivalent to q of x. It just scores under the base distribution. Questions about this? I don't expect you to necessarily get this 100%. This is, you know, implementation details. The critical part is that you understand what's going on with this, and the fact that you can either implement it by just computing these two terms separately, if somehow you keep track of what's continuous and what's not continuous or whatever, or you can just auto-diff this whole thing if you set things up in the way we just talked about. And if you did a web people style front-end language, which one of the projects is designing languages that allow you to do like extensions to Hopple and Fopple that allow you to do model learning and inference network learning, right? One way to do that is to build some sort of web people style language, which has a propose kind of thing. And if you were to implement propose using the full transformability everywhere, such that every distribution is in this framework, then your distribution library would have all of these functions, right? Which the reason why I stuck this in here is to sort of foreshadow a little bit about normalizing flows, because normalizing flows will allow you to compute all of these things, basically. So you can have very, very complex distribution types that are built into the language and baked in and just available to you as you go. So this implementation relies on a library of primitive distributions, which wrap a base distribution, a transformation that turns a sample from the base distribution to the sample from the given distribution, an inverse transformation that maps back, and a function that computes a log Jacobian determinant of the inverse transformation to compute the probability of a sample using change of variable, I should say here, in base distribution space. And in case you come back to this in the future, in the preceding slide, the dependence of all of these functions on the parameters of the densities are elided just because it's too much. It's like too much to write down. And I'm actually going to skip this because you can do this on your own if you want to, but this is basically going through and verifying that in this particular case, the discrete variables do the right thing and they get the right terms get killed off it's just a redo of the previous thing. So at the end of the day, what you end up computing under this formalism for the example program is the reparameterization trick for the discrete variable, and for the continuous variable, you end up computing the reparammed a variable gradient, just as you would expect. Okay. So that's it. Let's do a big recap. Okay. Model learning requires posterior samples. We have to integrate over the latent variables in the model in order to compute marginal likelihood. Right? We can't directly sample from the posterior distribution, so we use important sampling from some other distribution Q phi. In order to make learning efficient, Q has to be near P, and it has to be near P at all steps of this optimization. Right? Maximizing the elbow, the evidence lower bound, which is given here as EQ log joint over proposal, is one way to adapt Q to P by explicitly maximizing the marginal probability, or the lower bound on the marginal probability, which drives a KL to 0, and by operating on the elbow, we're pushing a KL to 0, which means that Q is close to the posterior distribution in this joint for a particular value of theta and lambda, right? If we make lambda be some function of the data and some parameters, right? Or what we have notationally done is just write it like this more frequently, right? If basically the proposal depends on y, then this becomes amortized inference, right? Particularly when you're in the IID data setting, fine. And it's really the only way that adapting Q to P makes sense for model learning. In particular, we want to jointly optimize the elbow, meaning that we want to optimize lambda while we're learning theta, or we want to optimize phi when we're learning theta. And if we're in the IID setting, then putting y in here is meta learning. If we're not in the IID setting, then the dependence on y will get ignored anyway when we're doing optimization. Fully reparameterizable Q leads to an efficient pathwise elbow estimator, where we don't have an expectation over Q, but we have an expectation over this not parameterized base distribution P epsilon, and we just replace X with the transformation of epsilon, which again, in general, will be dependent on Y and phi. That's a recap. The conclusion of today is that prob progs, higher order prob progs, deep prob progs, so on and so forth, basically where we ended up is the same as deep learning with random variables, discrete and continuous, right? They have the difference is that prob prog directly addresses the problem of having a mix of reparameterizable and non-reparameterizable distributions and control flow. That's that, you know, deep generative modeling, deep learning with random variables, and deep probabilistic programming are the same thing. The only differences are that we explicitly allow control flow, which most deep neural networks do not, with the exception of, say, for instance, reinforcement learning, which is one of the reasons why we will look at reinforcement learning as inference very soon, right? And of course, we specifically may allow for programs to consist of a mix of reparameterizable and non-reparameterizable distributions. So in other words, discrete and continuous distributions. A Hoppel trace, the thing that we want to take a gradient through, and we want to run auto grad on, is a stochastic computation graph with, in general, a sequence of reparameterizable and non-reparameterizable distributions. So in other words, one path through, you can evaluate the joint distribution, you can evaluate the gradient, but when you evaluate the gradient, you have to do it the way we talked about today, because you have this mix of discrete and continuous random variables. Today, we talked about basically a formalism, a framework that allows us to express reparameterized and non-reparameterable distributions in the same formalism. And using this formalism, we arrived at an autodiff compatible deep probabilistic programming loss, which is just EQ tilde, where we've made Q tilde either, a base type or with parameter phi, or a base type that has no parameter phi. And then log of this, which has just got the reprogrammed version of X in it. Right? And this is autodiff compatible, and you're off to the races, right? Which computes the reinforced or reprogrammed partials as appropriate, automatically zeroing gradient paths on a per address or random variable type basis. This is within reach for you to implement given what you have, which is completely amazing, right? I'll address this in just a second, Vasilios. So obviously note, just to remind you, this has really all been about model learning, right? And what we're doing is we're trying to set up a joint optimization problem so that we can do model learning, because we can learn an inference network that keeps up with the model so that it approximates the posterior at a particular model parameter value, right? But this loss is imminently compatible with learning of theta, because you can just straightforwardly differentiate this thing with respect to theta. There's the partial comes inside the expectation, no problem, and it's just maximum likelihood. Note that in general, when you see this stuff written out in the literature, that of course the model can be reparameterized too, and you've already seen this in your homework when you transformed random variables into the parameterizations of random variables into unconstrained spaces, so that you could do unconstrained optimization, right? So this kind of reparameterization also applies to the model, right? So if you have a reparameterization of the model, that is totally fine too. And now, in addition to doing inference, which you can do in Pyro or TensorFlow Probability or Gen or Turing.jl or something like that, if you were somehow magically to be able to cast your problems as inference problems, you would be able to put them into these packages and do inference. But also, these packages all allow you to do simultaneous model learning and inference network learning. And what we just talked about today is what the most advanced Prob Prog systems do. It's this, single objective for dealing with reparameterizable and non-reparameterizable distributions. Right? You could, again, as a project, implement this in your evaluator. And the challenge in teaching this subject in a coherent way is that we could just start with this and then talk about uses. That's one way of doing it, but that would be a deep learning course. Or we have to talk about languages and how to evaluate them and so on and so forth. And that gives you a sense of what the trace structure is and so on and so forth. One issue with the languages that you've seen in the book is that, for instance, they don't have language constructs for identifying model parameters. They don't have hooks for computing losses directly. And in the case of IID data, they don't have an outer data loop. So these are interesting language design projects that you could think about undertaking. And I think that's it. So Vasilios, if we can use, how about you speak? You're very quiet, Vasilios. So why don't you let your dulcet tones ring out amongst the class?
So you want me to read this?
Or? Sure, yeah. Or just ask your question. Yeah.
Yeah, basically the question is like if we can use a parameterizable approximation of a discrete distribution, such as the Gumbel softmax. Is this like kind of our default choice instead of doing likelihood ratio estimation, because we said that it's more sample efficient?
So Gumbel softmax makes literally no sense in the Prob Prog context.
Okay. It's as far as I know, it's a trick to make a discrete distribution
So if
in a way that can be used to reparameterize it.
Yeah, so if you'll notice how the Gumbel softmax works, it only allows you to basically draw a one-hot vector in some space,
Indeed.
right?
Indeed, yeah.
But the whole point is that that one-hot vector is not actually a one-hot vector.
Indeed, yeah.
Okay, which means that, for instance, if you were to, for instance, try to use that in the execution environment of a Prob Prog, in other words, I'm expecting a one-hot vector, right? So if one-hot vector 1 index is 4, do this. If one-hot vector index is 5, do this. So a case statement based on the one-hot vector,
Yeah.
right, will lead to a different control flow path and a different trace. So the thing about the concrete distribution or the Gumbel softmax trick or whatever is that you don't actually get a one-hot vector.
Yeah, you get something very, very close to the work.
Yeah, but it's not a one-hot vector. So that means
you cannot index.
Absolutely not. So you can't do it is an invalid program state immediately. So you can't actually. So what the implication is one way to look at it is that you should evaluate all control flow paths that have non-zero weight and weight them according to the weighting under the Gumbel softmax. The problem is that all paths have non-zero weight. So the Gumbel softmax in the discrete context says evaluate all paths simultaneously. And this is not possible in a control flow context, right? It's only possible in a deep neural network where you're expecting a one-hot, but you're okay if that vector that you pass through whatever other vector computations you compute later on lives in RD instead of 0, 1 to the D.
I see.
Does that make sense?
Yeah.
That's an excellent question. In fact, actually, that is the basis of the paper revisiting reweighted wake sleep for stochastic control flow models. Basically, the entire point of that paper is that you can't do the Gumbel softmax trick when you actually have stochastic control flow. It's invalid, right? So in that case, maybe actually reweighted wake sleep isn't such a bad thing to do.
Yeah, thank you.
Yeah, of course. Good, excellent question.
Can I ask a question?
When have I said no?
No, you've never said no. It's just a way to announce that I'm going to ask it.
Yeah,
you know what? I'm going to ask a question.
There you go. Awesome.
The deep here, like we haven't talked about anything that's, I'm assuming that implies deep neural networks somewhere, right? But like, is that just, if your lambda is a deep neural network, is that what deep implies?
So the point, I actually got really pissed off when the name deep probabilistic programming came into being, because there's nothing that is. It's a cute phrase, right? But what it really means is that your model and your inference network can be partially specified, right? And in particular, the link functions in both the model. So I've highlighted a few of them here, right? The link functions in both the model and in the inference network can be arbitrary deep neural network functions. So I think it's worthwhile thinking, and we'll start to see some examples of this as we go on. That in particular when we talk about meta learning, like the real power of like Prob Prog came out of the land of inference, right? And thinking that uncertainty calculus is important, right? You can agree with that or not agree with that. That's totally fine. deep learning came out of the land of, nonlinear function approximation is important and screw uncertainty, right?
Mm-hmm.
When we mash these together, we can call it whatever you want. You can call it deep learning with uncertainty. You can call it deep probabilistic programming. You can call it deep generative modeling, so on and so forth. The point is that the model is only specified up to structure, and the inference network. And in order to actually learn in such a model, you must have an inference network that you're simultaneously learning. Otherwise, the posterior inference problem is totally impossible, right? So you can also call this field structured VAEs. They're, as far as I'm concerned, they're really all the same thing, and it really all boils down to, honestly, this thing right here, right? If you don't want control flow, then you can use Gumpel softmax. If you want control flow, then you have to do this objective, and if you want structure. Right. And the question is, can you build programming languages tools to do this? And the answer is yeah, and they come in the form of Pyro and whatever, right? Or you just directly implement this loss, right? Which is quite often proves to be simpler in languages like PyTorch or TensorFlow probability.
And the theta that you had in the last slide, the model parameters, like if I think of the sort of simple probabilistic programs that we've written so far, that theta would just imply sort of the parameters that we've had in the link functions.
Yeah, they would be in the simple problems we've had in the simple programs that we've looked at so far. They would be the parameters of the prior in almost every case, right? So
Yeah,
there's some prior parameterization. There are some numbers that we stuck in there. We don't know what those are, right? We haven't had many link functions, right? But you in this particular case, in the Bayesian neural network case, this is why I started with that as well. You could reformulate that so that so that all the parameters in that network are model parameters.
Mm-hmm. Okay.
Jason, you're either looking at Reddit or you're thinking about clicking the button and asking a question. I'm guessing Reddit, but
actually, I'm not on Reddit, but I did have a question, which is I wasn't gonna actually ask it, but can you reliably do batching in any systems with control flow?
no.
Okay, so I guess all these Prob Prog systems don't have any kind of like batching mechanism built in.
They do, as you know, since you've played, but it's also one of the most horrible parts of all of them, right?
Yeah, it was not nice.
Huh?
It was not nice because I think it only had batching for certain like inference methods and not others, and it was really annoying.
Yeah. It's complicated. Yeah. Control flow does make things complicated. More questions? More comments? Concerns? Criticisms? Happy to be done with it?
So control flow and reparameterization is not an issue, but batching, I'm just trying to unpack that a little bit more. It kind of makes sense because like you don't want two samples.
So before you assert to the first and have people remember this somehow. So control flow is still problematic for gradient-based optimization as well, right?
Pardon me?
Which is to say, right, we're computing a gradient at a particular setting of the on a particular trace, at a particular setting of the value of x, basically, right? And there's still discontinuities because of control flow. So it's still uncomfortable. right? But we can do great. I mean, I've got a valid gradient at this particular point in X space. Okay, right. But there's still discontinuity. So gradient-based optimization is still complicated. That's all I can say, right? You take a step in model space. Who knows? All right, Mia, I feel somewhat flattered that you've decided to put yourself in a similar situation to me. I think it's, imitation is the something about flattery. I don't know, imitation, yeah, but all right, if that's that, that's that. When's the homework due?
In a week.
Sweet. Okay. Do be thinking about projects.
Will there be a late submission box open for homework 6, like homework 5?
You know, I think we're going to make the the greatest hits mix of payment asking for extensions on the homework. We will see what happens next week. Try it. There's a lot of support code for it. You just have to think. Okay, thank you very much for your time and attention. Look forward to seeing you next week. Cheers.
Thanks, Frank.
Bye.
Nice.